Hello there and welcome. Tonight we're diving into something that sits right at the edge of everything we know about computing, about information, about the way machines can think. And honestly, the more you understand about quantum computers, the more you realize that they don't think like every other computer we've ever built. Not just faster, not just more powerful. They think in a fundamentally different way. A way that would seem impossible if it weren't rooted in the actual laws of physics. The quantum realm operates by completely different rules than the world we see every day. And quantum computers exploit those rules to do things that classical computers simply cannot do, no matter how many processors we throw at them. This isn't about incremental improvement or better engineering. This is about a different paradigm entirely. And to understand how quantum computers think differently, we first need to understand how every computer you've ever used actually thinks. Because once you see that contrast, once you really grasp it, the quantum world stops being abstract and starts becoming clear. So let's begin with the foundation. Let's talk about the computers we know. Let's understand the binary world before we venture into the quantum realm. Classical computers are everywhere. They're in your pocket, on your desk, running the entire infrastructure of the internet. They're in the servers that store everything you do online. They're in the cars you drive, the hospitals that treat you, the power plants that light your home. And they all think the same fundamental way. They think in binary. Everything they do, every calculation, every image you see, every word you read, it all comes down to ones and zeros. That's it. That's the entire foundation. A bit is either 0 or it's 1, off or on, false or true, high voltage or low voltage, magnetized or demagnetized. There are only two possible states. And that simplicity, that binary foundation, is actually why classical computers work so well. Because if something can only be in one of two states, you can control it, predict it, and verify it with absolute reliability. And that reliability is why we trust our computers with our bank accounts and our private messages, and literally the safety systems that keep planes in the sky. Now here's how a classical computer actually creates those bits. Inside every processor, there are transistors. Transistors are tiny electronic switches. When you apply voltage to the base of a transistor, electricity flows through it. That's a 1. When you remove the voltage, the current stops. That's a 0. It's simple, it's elegant, and you can do it billions of times per second. Your laptop probably has billions of transistors, each one switching on and off in precise patterns to execute the instructions you give it. And because transistors are so reliable, because they can be manufactured at massive scales, because the physics is well understood and predictable, classical computers have become incredibly powerful. A modern processor might contain tens of billions of transistors, and they work in perfect synchronization. Every transistor knows its job. Every bit knows its state. There's no ambiguity. There's no uncertainty. That's the beauty of binary logic. But there's a crucial thing about classical bits that limits them. At any given moment in time, a classical bit is either 0 or 1, not both. Never both. Not in some fuzzy quantum way, not in some probabilistic sense. It is definitively one or the other. This deterministic nature means that a classical computer must process information sequentially or through parallel processing, where multiple operations happen simultaneously on different cores. But fundamentally, each bit exists in one definite state. If you have a problem that requires exploring a million possible solutions, a classical computer must check them one by one, or divide them up among multiple processors, but it's still essentially checking possibilities sequentially. And for certain types of problems, that's not just slower, It's exponentially slower. It's practically impossible. Think about what a classical computer does when it processes information. It takes your input, it performs a calculation according to an algorithm, and it produces an output. Every step is deterministic. Every step follows a logical path. You give the same input twice, you get the same output twice. Always. This is wonderful for most things we use computers for. Banking, email, word processing, all of these benefit from that determinism. You want your data to be reliable. You want the same result every time. You want to know that when you save a file, it stays saved exactly the way you left it. That when you send an email, it arrives intact. That when you transfer money, the calculation is exact. The classical computer's determinism is not a limitation for these tasks. It's a feature. It's essential. But for certain problems, this step-by-step, one path at a time approach becomes a serious limitation. Imagine you're trying to find the prime factors of an enormous number, a number with hundreds of digits. To a classical computer, this is a nightmare. There are so many possible factors to check, so many combinations to test, that even the fastest supercomputer would require longer than the age of the universe to crack it. That's not exaggeration. That's the actual mathematics. Similarly, imagine you have an unsorted database of 1 billion items, and you're looking for one specific item. A classical computer has to check them one at a time, on average needing to check 500 million items before finding the one it's looking for. It's not that the computer is slow, it's that the problem space is exponentially larger than the classical approach can efficiently handle. And then there's the matter of how classical computers scale with problem complexity. If you double the size of a problem, you typically need exponentially more computing power to solve it using classical approaches. A problem of size 10 might take 100 units of time. A problem of size 20 might take 1,000,000 units of time. A problem of size 100 might take more time than atoms exist in the universe. Some problems grow so complex that even the most powerful supercomputers in the world would take longer than the age of the universe to solve them. Not because the computers are slow, but because the problem space is so vast, and classical computers can only explore it one path at a time, one possibility at a time, one state at a time. There's a fundamental mismatch between the way why classical computers think and the way certain problems are structured. Classical computers are excellent at what they do, but they're limited by their very nature. And that mismatch is why quantum computers step in with something completely different. Now quantum computing starts from a completely different place. Not from the deterministic world of transistors and binary logic, but from the quantum mechanical world where particles behave in ways that defy our intuition, where things can be in multiple states simultaneously, where observation itself changes reality, where particles that are separated can be mysteriously connected, where the very act of measuring something forces it to become something definite, even though before measurement it was something else entirely. And when you harness those quantum mechanical properties, when you translate them into computing logic, when you build machines that operate according to quantum rules rather than classical rules, you get something that doesn't just work differently. It thinks differently. It approaches problems from a fundamentally different angle. It processes information through a lens that classical systems cannot access. In the classical world, everything follows a path. Water flows downhill through a clear channel. Electrons move along a wire, following Ohm's law, predictable and deterministic. Light travels in straight lines, or curves around objects according to the laws of geometric optics. Cause leads to effect in a clear, linear way. An event happens and from that event flows a consequence. That consequence flows into the next consequence. Classical computers work the same way. Input leads to processing, leads to output. Each step follows from the previous one. But in the quantum world, particles don't follow paths. They don't have trajectories like we imagine them. They exist in a state of possibility until something observes them. An electron doesn't orbit an atom like a planet orbits the sun. It exists in a cloud of probability around the nucleus. The electron is not in a specific location, any more than it has a specific velocity. It has a probability distribution for position and a probability distribution for momentum. You can't ask where it is without fundamentally changing what happens next. The act of measuring where the electron is changes its momentum. The act of measuring its momentum changes its position. You can't predict its future without accepting that before measurement, it's not in any single state at all. This is the foundation on which quantum computers are built, not on transistors and binary logic, but on the rules of quantum mechanics that govern particles at the smallest scales. And those rules are profoundly different from the rules that govern our everyday experience. They're alien to our intuition. They're counterintuitive in almost every way, but they're also absolutely, demonstrably real. We've tested them for 100 years. We've built technologies on top of them. We've confirmed them to incredible precision, and now we're building computers on them. The basic unit of quantum computing is the qubit, which stands for quantum bit. And here's where everything changes. A classical bit is either 0 or 1. No in between, no flexibility, no ambiguity. But a qubit can be 0 or 1, or both 0 and 1 at the same time. That simultaneous existence is called superposition, and it's not just a minor variation on classical computing. It's not an engineering improvement. It's not a faster version of the same idea. It's a fundamental paradigm shift in how information is represented and processed at the most basic level. When a qubit is in superposition, it exists in a weighted combination of both states. Not undefined, not unknown, not in some vague, uncertain way, but genuinely in both states at once, with certain probabilities for each. The mathematics describes it precisely. The physics makes it real. This is one of the strangest things about quantum mechanics. In our everyday experience, nothing behaves this way. A light switch is either on or off. A coin is either heads or tails. A person is either in the room or not in the room. We never see things in multiple states simultaneously. And yet, at the quantum level, particles regularly exist in superposition. Electrons are in multiple places at once. Photons take multiple paths. Qubits embody both 0 and 1 until measurement forces a choice. This is also the key to quantum computing's power. The moment you have a qubit in superposition, you have something classical bits cannot give you. You have genuine parallelism, not simulated parallelism, not multiple processors each working on different pieces. Actual parallelism, where a single quantum system explores multiple possibilities at the same time. Now you might be thinking, well, how can something be in two states at once? That violates everything we know about how the world works. And you're right. It violates everything we know about how the classical world works. But at the quantum level, particles don't follow classical rules. An electron can exist in multiple energy states simultaneously. A photon can travel multiple paths at once. A qubit, which is typically implemented using the properties of atoms or photons or superconducting circuits, can genuinely exist in a superposition of 0 and 1. And when you measure it, when you look at it, when you force the quantum system to give you a definite answer, the superposition collapses. You get a definite result, either 0 or 1. But before measurement, before you force the question, it's both. It's neither. It's something that doesn't map onto classical categories at all. This is where the power starts to become apparent, and where the thinking really becomes different. Imagine you have 3 classical bits. They can represent one of 8 possible values at any given time. You could represent 0, 0, 0, or 0, 0, 1, or 0, 1, 0, all the way up to 111. But at any single moment, you're only looking at one of those 8 possibilities. To check all 8, you'd need to run 8 separate computations, or use 8 separate processors working in parallel. You could divide the work among them, but you still need to check them. Now imagine you have 3 qubits in superposition. Those 3 qubits can represent all 8 possible combinations simultaneously, all at once, in parallel. You're not checking them one at a time. You're not even dividing them among different processors. You're exploring the entire solution space in a single quantum operation. A single operation. All 8 states existing in superposition, all being explored at the same time. And this advantage doesn't grow linearly. It grows exponentially. This is crucial. With 1 qubit in superposition, you can represent 2 states at once. With 2 qubits in superposition, you can represent 4 states at once. With 3 qubits, 8 states. With 4 qubits, you can represent 16 states simultaneously. 5 qubits give you 32 states in parallel. The scaling is exponential. Add 1 more qubit, and you double the number of states you can explore at once. But here's where it gets mind-bending. 100 qubits in superposition can represent more states than there are atoms in the observable universe, all at the same time, all being explored in parallel, all contributing to the calculation, all part of a single quantum state. A classical computer with 100 classical bits could also represent that many different numbers, but only one at a time. To explore all possible values, it would need to run 100 computations in sequence, or use 100 processors working separately. But 100 qubits in superposition represent all those states in one coherent quantum system. That's the difference. That's where the exponential advantage comes from. But here's the crucial thing that really separates quantum from classical thinking. Superposition is not the same as running a classical computer in parallel. It's not about having lots of processors each checking different possibilities. That's still the classical paradigm, just distributed. Superposition means the quantum system is genuinely exploring all those possibilities at once in a single coherent quantum state. The qubit is not secretly one or the other, and we just don't know which. It's not that 0 and 1 exist separately, and we're uncertain. It's both, mathematically and physically, existing together until the moment of measurement collapses that superposition. And that's a completely different way of processing information. The classic maze analogy helps capture this. You're standing at the entrance of an enormous maze, and you need to find the exit. A classical computer is like a person who must physically walk down each pathway. They try one direction, hit a dead end, back up, try another direction, hit another dead end, back up and try yet another direction. They might split into multiple copies of themselves to explore different paths in parallel, each copy walking their own path, but ultimately, each copy must physically walk each path and report back. If there are 1,000,000 possible paths, checking them all takes time proportional to 1,000,000 checks. A quantum computer is different. It's like a ghost that can walk all the paths at once, not just very quickly, actually walking all of them simultaneously in superposition. The quantum computer exists in a superposition of all possible maze solutions. It explores every path at the same time. The ghost walks down all 1,000,000 paths at once, and none of them, all in a single quantum superposition. But then, here's the trick. The clever part, where quantum computing gets smart. When the quantum computer checks the answer, when it measures the result, the superposition collapses and it reveals the correct path. But it doesn't just randomly pick one of the million paths. Through a process called quantum interference, which is fundamental to how quantum algorithms work, the quantum computer can arrange things so that incorrect paths interfere with each other and cancel out, while the correct path has constructive interference and becomes the most likely outcome. So when the superposition collapses, when measurement forces the quantum state to become classical, it's much more likely to reveal the right answer than any wrong answer. This exponential advantage from superposition is fundamental to why quantum computers think so differently. A classical computer solving a problem of size n typically requires time proportional to n, or maybe n squared or n cubed, depending on the algorithm and how complex the problem is. For some problems, the time grows exponentially with n, making them impossible for large values. A quantum computer solving certain types of problems can do it in time proportional to the square root of n, or even in polynomial time instead of exponential time. For large problems, this difference is not just an improvement. It's not like going from a fast car to a faster car. It's a revolution. It transforms problems that are computationally impossible on classical systems into problems that become solvable. A problem that would take a classical computer 10,000 years to solve might take a quantum computer a few hours. That's not an engineering improvement. That's a fundamental shift in what's possible. The key word here, the important caveat, is certain types of problems. Quantum computers aren't universally faster than classical computers. They're not better at everything. You wouldn't use a quantum computer to browse the web or write a document or do email. Classical computers are still better for most of what we do. They're reliable, they're predictable, they're efficient at the things they're designed for. But for specific problem classes, for problems that involve searching large spaces or factoring large numbers or simulating quantum systems, quantum computers' ability to explore superposition of possibilities simultaneously creates an advantage that classical computers simply cannot match, no matter how many transistors or how much parallel processing you throw at them. No amount of classical parallelism can bridge that gap. It's a fundamental difference in computational approach. It's not evolution. It's revolution. It's a different way of thinking about problems entirely. And this is where we're really starting to see how quantum computers think differently from every other computer ever built. They don't think step by step. They don't think in terms of explicit pathways through a solution space. They don't enumerate possibilities one at a time, or even in parallel across multiple processors. They think in terms of quantum states that embody multiple possibilities simultaneously. They leverage the strange rules of quantum mechanics to explore vast solution spaces in ways that classical logic cannot. And superposition is just the beginning. There's also entanglement, which creates mysterious correlations between qubits. There's quantum interference, which amplifies correct answers and cancels out wrong ones. There's the collapse of the wave function when you measure, which transforms superposition into definite classical states. All of these quantum mechanical properties work together synergistically to create a computational paradigm that is fundamentally different from classical computing. Superposition is so powerful precisely because of this exponential scaling. Let's think about what this means in practical terms. Suppose you want to find a specific needle in a haystack. A classical computer, no matter how fast, must check each straw one by one. It picks up a straw, looks at it, puts it down, picks up the next straw, looks at it, puts it down. For a haystack with 1 billion straws, it might need to check 500 million straws on average before finding the needle. But a quantum computer in superposition is examining all the straws simultaneously, all at the same time. It's asking about all of them at once. This is not a metaphor. This is not theoretical. This is what actually happens at the quantum level. Or consider trying to find the shortest path through a network of cities, a problem known as the traveling salesman problem. With classical computers, you might need to check millions or billions of different routes. But with quantum superposition, you're exploring all those routes in parallel within a single quantum state, all at once. With classical computers, doubling the number of cities might increase the calculation time by years or more. With quantum computers, it might barely increase the calculation time at all, because you're exploring the space more intelligently through superposition, examining all routes simultaneously. The reason this works is that superposition allows quantum computers to process information in a way that mirrors the structure of the problem itself. Many problems have this exponential structure built in. There are two choices at each step, two possibilities that branch into 4, which branch into 8, which branch into 16. A classical computer must address this branching sequentially. A quantum computer in superposition addresses it all at once. It's why certain problems that seem impossibly hard for classical computers become tractable for quantum computers. Now, when we talk about a qubit in superposition, we're talking about something precise. It's not vague or hand-wavy. The mathematics of quantum mechanics describes exactly how the superposition works. A qubit in superposition is described by what's called a wave function, or state vector. This mathematical object contains all the information about the qubit superposition. It specifies the probability of getting a 0 versus a 1 when measured. But more than that, it specifies the quantum phase, the relative timing and alignment of the 0 and 1 components. And that phase information is crucial for making quantum algorithms work. That's what allows quantum interference to happen, allowing correct answers to amplify and wrong answers to cancel out. Before measurement, the qubit genuinely exists in both states. After measurement, it collapses into one or the other. This isn't because we didn't have enough information before. It's not that the qubit was secretly in one state and we just didn't know it. That's actually a fundamental misunderstanding of quantum mechanics that took physicists decades to fully grasp and accept. The qubit is not in a hidden definite state before measurement. The superposition is real. The qubit is in both states until measurement forces a resolution. This is deeply different from how classical systems work. In a classical system, when you don't know the state of something, that's a limitation of your knowledge. The state is already determined. You just don't know what it is. It's like a coin that was flipped and landed before you looked at it. It's definitely heads or definitely tails. You just don't know which. But you can, in principle, find out by looking. The state was always determined. But in a quantum system, when something is in superposition, the state itself is genuinely undetermined. It's not just that we don't know, it's that there is no definite value until measurement occurs. The qubit is not secretly a 0 or secretly a 1 with us just not knowing which. It's actually both. It's actually neither. It's in a quantum state that doesn't map onto classical categories. This is one of the most conceptually challenging things about quantum mechanics. It took physicists decades to fully accept this. The reality is even stranger than it sounds, but it's also what makes quantum computing possible. It's this fundamental weirdness that quantum computers exploit. The implications are staggering. If you have a quantum computer with 300 qubits in superposition, it can represent more states simultaneously than there are atoms in the universe. With 500 qubits, the number becomes incomprehensibly large, utterly beyond human comprehension. And all of these states are being processed in parallel, all at once, in a single quantum system. No classical computer could come close to this kind of parallelism, no matter how many processors you added. You could add 1 billion processors, 1 trillion processors, and you still wouldn't match the parallelism of a 500-qubit quantum computer. It's not even in the same category of comparison. It's not that one is faster than the other. It's that they're operating on fundamentally different principles, exploring solution spaces in ways that are incompatible with classical logic. This is what makes quantum computers think so differently. They don't think like we think. They don't think like the classical computers we've built. They think the way quantum systems naturally think, according to the rules of quantum mechanics. They explore vast spaces of possibilities simultaneously. They use wave-like interference patterns to amplify correct answers and cancel out incorrect ones. They exploit entanglement to create correlations between qubits that classical systems cannot achieve, no matter how clever the engineering. They operate at the boundary between possibility and reality, where superposition reigns until measurement forces a choice. They leverage the uncertainty principle and the wave-particle duality. It's an alien way of thinking, rooted in a physics that doesn't match our everyday experience, but absolutely fundamental at the most basic level of reality. And understanding this different way of thinking, this different computational paradigm, is key to understanding why quantum computers represent such a radical departure from everything that came before. Of course, there's a catch. There always is. When you measure the superposition, it collapses. You get one answer, just one. One of all those possibilities becomes real, and the superposition disappears. The ghost that was walking all the paths at once is forced to become a person standing in one location. The wave function collapses. The possibility becomes actuality, and you get a definite outcome. So how do quantum computers actually solve problems? How do they use this incredible parallelism to get useful answers if measurement just gives you one random answer? The answer is quantum algorithms, carefully designed sequences of operations that manipulate the superposition so that wrong answers interfere destructively and cancel each other out, while correct answers interfere constructive, lie, and become amplified. When the superposition finally collapses through measurement, the answer that emerges is much more likely to be the right one. The quantum algorithm choreographs the interference patterns. It arranges the probability amplitudes. It guides the quantum state through a sequence of transformations that favor the correct answer. This requires incredible precision. The quantum algorithms must be designed with exact knowledge of how the superposition will evolve. A single error, a misalignment in the phase relationships, and the interference patterns could be inverted, making the correct answer less likely instead of more likely. This is one of the challenges of quantum computing. The algorithms must be perfect. The gates must execute with high fidelity. Any errors accumulate and corrupt the results. But when done correctly, when the quantum algorithm is properly designed and the quantum gates execute with sufficient precision, the result is a massive speed-up for certain problem classes. Problems that would take classical computers years or centuries can be solved in minutes or hours on a quantum computer. This is where quantum computers truly think differently. Classical computers solve problems through explicit logic. They check conditions, follow branches, execute algorithms step by step. Quantum computers solve problems through amplification and cancellation. They manipulate probability amplitudes. They use interference. They exploit the wave-like nature of quantum systems. It's a completely different computational paradigm. Consider a classical search problem. You have a database of 1 billion items, and you want to find one specific item that satisfies some condition. A classical computer has to query the database one item at a time. In the worst case, the item you're looking for is the last one checked. On average, you'd need to check 500 million items before finding it. A quantum computer using superposition can query all items simultaneously in a superposition, but then it needs to amplify the probability of the correct answer. It does this through a process where the correct answer interferes constructively with itself, becoming more probable, while wrong answers interfere destructively with each other, becoming less probable. When measurement occurs, the result is much more likely to be the correct item. Or consider the problem of finding patterns in massive amounts of data. Classical computers can process data quickly, but fundamentally, they process it sequentially or in parallel across multiple cores. A quantum computer in superposition can examine many patterns simultaneously, allowing it to find correlations and patterns that might be hidden in classical analysis. This is why quantum computers are particularly powerful for machine learning applications where you're searching for patterns in data. The way quantum computers think about these problems is fundamentally different from how classical computers approach them. Classical computers use logic. Quantum computers use probability and interference. Classical computers eliminate possibilities one at a time. Quantum computers amplify correct possibilities and cancel out wrong ones. It's not just a speed difference, it's a different mode of thought entirely. Quantum computers aren't just faster classical computers. They're not just parallel processors with more cores. They're not an evolutionary step forward from the classical paradigm. They're machines that harness the quantum mechanical nature of reality itself to process information in ways that classical physics simply cannot match. They think in superposition, exploring multiple possibilities simultaneously. They think in entanglement, creating correlations between qubits that have no classical equivalent. They think in probability amplitudes and wave functions and quantum interference. They manipulate the fundamental nature of quantum states to solve problems. They think the way the universe itself thinks at the most fundamental level, operating according to the deep laws that govern reality at the atomic and subatomic scales. And that's what makes them so radically, fundamentally different from every computer we've built before. It's not about being faster or having more memory or more processing power. It's about thinking in a completely different way, accessing a different computational realm entirely, exploiting the weirdness of quantum mechanics to achieve what classical computing cannot. There's another layer to this quantum thinking, another dimension that makes quantum computers even more alien to our classical understanding. It's called entanglement, and it's one of the most profound and strange features of quantum mechanics, the one that even makes physicists uncomfortable. Because superposition alone isn't the whole story. Superposition gives quantum computers the ability to explore multiple possibilities simultaneously, but it's entanglement that weaves those possibilities together in ways that have no classical equivalent. It's what allows quantum computers to think in correlations and connections that classical computers simply cannot access, no matter how cleverly they're engineered. Imagine you have two classical bits. Each bit is independently 0 or 1. They're separate, independent. They don't influence each other in any way. You can change one bit without affecting the other in the slightest. Two classical bits can represent 4 different states, but only one state at a time, 0, 0, or 0, 1, or 1, 0, or 1, 1. You pick one and the other bits maintain their values exactly as they were. They're just sitting there, storing their information independently. There's no mystery here. There's no weirdness. It's straightforward and predictable and makes perfect sense to anyone who's ever used a classical computer. But now imagine you have 2 qubits and they become entangled. This is where quantum mechanics gets genuinely strange. When two qubits become entangled, their states become linked in a way that seems to violate everything we know about how separate objects should behave. Everything we've learned from our experience in the classical world. Everything that makes sense. Here's what entanglement actually means, and try to keep an open mind, because this is where physics gets truly counterintuitive. If you have two entangled qubits, and one of them is measured to be 0, the other qubit will instantly be 1. Not almost instantly, not faster than light in some impossible way, not in some hidden way that we just don't understand yet. Instantly, right now, this instant. The moment you measure the first qubit and get 0, the second qubit becomes definite as 1, simultaneously, and this happens regardless of how far apart they are. They could be separated by entire galaxies, by the entire width of the observable universe, and the correlation would still be instant. Einstein called this spooky action at a distance because it bothered him so much. He was deeply disturbed by it. He thought there had to be some hidden variable, some information that was somehow carried between the qubits through some mechanism we just didn't understand. But experiments over the past 100 years have repeatedly confirmed that there is no hidden variable. The entanglement is real. The correlation is genuine. Measuring one qubit instantaneously determines the state of its entangled partner, no matter the distance between them. No classical mechanism can explain it. It just happens. But here's the thing that makes this even stranger and even more remarkable. Before measurement, neither qubit has a definite state, not even secretly or hidden from our view. They're both in superposition. The first qubit is in a superposition of 0 and 1. The second qubit is also in a superposition of 0 and 1. But they're entangled, which means their superpositions are linked. Their destinies are intertwined. If you measure the first qubit and get 0, the superposition of the second qubit collapses to 1. If you measure the first qubit and get 1, the superposition of the second qubit collapses to 0. But before you measure, they're not secretly one or the other. They're not hidden classical states that we just don't know about. They're genuinely in superposition together, linked through entanglement, existing as a single quantum state that spans both qubits. Impossible to separate or describe independently. This is the fundamental mystery of entanglement. Not that the outcomes are correlated, because that would be classical correlation, but that before measurement, there are no outcomes at all. There's just entanglement. This is completely different from classical correlation. It's not even in the same category. Two classical bits can be correlated. If you program them so that one is always the opposite of the other, then learning the state of one tells you the state of the other. Simple, straightforward. But classical correlation works through explicit information. The correlation was established by the program. The bits maintain independent values. The correlation is a consequence of how we set things up. In quantum entanglement, the correlation is fundamental to the nature of the system itself. The qubits don't have independent states. They don't have separate values that we're just not aware of. They exist as a single shared quantum state. The correlations are not programmed in from outside. They arise from the quantum nature of the system itself. This is a difference that goes right to the heart of what reality is at the quantum level, and this has enormous implications for quantum computing. When you have many qubits and they become entangled, you're not just increasing the number of independent quantum states. You're not just adding more processing power in some linear way. You're creating a single quantum state that encompasses all of them together, with correlations linking all the qubits, with every qubit connected to every other qubit through quantum mechanical correlations that have no classical parallel. The power grows exponentially. With 3 entangled qubits, You're not just representing 8 states in superposition, each independently explored. You're representing a single unified quantum state, where all 8 states are connected through entanglement, where measuring one qubit instantly constrains all the others, where the correlations between them are fundamental to the calculation itself. The computational power available to you scales not linearly, but exponentially with the number of entangled qubits. Add one more qubit, and you double the potential computational capacity. This exponential scaling is where the advantage of quantum computers really comes from, where the revolution happens. This is why entanglement is so crucial to quantum computing, more crucial even than superposition, because while superposition gives you parallelism, entanglement gives you correlations that allow that parallelism to be exploited in profound ways. Entanglement creates correlations that allow that parallelism to be exploited in profound ways. Entanglement creates correlations that classical systems cannot replicate. These correlations allow quantum algorithms to explore solution spaces in ways that exploit the structure of the problem, ways that classical enumeration simply cannot achieve. When qubits are entangled, operations on one qubit affect all its entangled partners simultaneously. This cascading effect allows quantum algorithms to propagate information through the entire system in ways that classical computers cannot achieve, even with unlimited parallel processing, even with billions of processors. Consider what happens during a quantum calculation. From the very beginning to the very end, you start with your qubits in a known initial state, usually all zeros. They're separate, independent. No correlations exist yet. Then you apply quantum gates, which are operations that transform the quantum state. These gates can create superposition, spreading qubits across multiple states at once. They can create entanglement, linking qubits together, making their fates dependent on each other. As the calculation proceeds, more and more qubits become entangled with each other, their states becoming increasingly linked. You're building up correlations throughout the quantum system, layer by layer, gate by gate. Each gate adds new connections, new correlations, weaving the qubits together into increasingly complex patterns. By the time you measure the final result, all these correlations have been shaped and molded by the quantum gates, guided by the quantum algorithm, arranged to amplify the correct answer while cancelling out incorrect ones through quantum interference. The beauty of entanglement from a quantum computing perspective is that it allows you to process global properties of a system without explicitly checking every state. A classical computer solving the traveling salesman problem must examine each route separately, checking the length of each possible path. Even with parallel processing across multiple cores, you're still checking routes individually, still examining separate possibilities one after another. But a quantum computer with entangled qubits can represent all routes simultaneously in a single quantum state. Through entanglement, information about good routes and bad routes is shared across the entire system. The quantum gates can manipulate this global state in ways that privilege routes with desirable properties, ways that amplify the probability of finding optimal routes while suppressing the probability of poor routes. It's not that the quantum computer checks all routes faster, it's that it doesn't have to check them one at a time at all. It checks them all in parallel, through the magic of entanglement and interference, and quantum superposition. Entanglement also enables what's called quantum non-locality. This is the property that makes quantum mechanics so fundamentally different from classical physics. So fundamentally different from everything we understand about how the world works at everyday scales. In classical systems, if two objects are separated, they cannot instantly affect each other. Information travels at the speed of light at most. Nothing can travel faster. This is a core principle of relativity. the bedrock of modern physics since Einstein. But in quantum systems, entangled particles do exhibit instant correlations, not instant transmission of information, which would violate relativity and causality and everything we know about physics, but instant correlation of measurement outcomes. When you measure one entangle, ed particle, the other behaves accordingly immediately, as if they were communicating instantaneously. This non-locality is not some loophole or misunderstanding or consequence of incomplete knowledge. It's been tested and confirmed experimentally thousands of times in laboratories around the world. It's as solid as any physics gets. It's a genuine feature of nature at the quantum level. And quantum computers exploit this non-locality to achieve correlations between qubits that classical computers cannot match, that no classical system could possibly match. The challenge of maintaining entanglement is one of the great obstacles in building practical quantum computers, maybe the greatest obstacle of all. Entanglement is fragile. It's delicate. It's fragile like a soap bubble is fragile, or like a house of cards, or like trying to balance on a tightrope while the wind is blowing. Any interaction with the environment can destroy it. Any noise, any stray electromagnetic field, any vibration, any heat, any measurement, anything at all can cause the qubits to decohere, losing their entanglement, collapsing their superposition, destroying the carefully constructed correlations that the quantum algorithm has painstakingly built. This is why quantum computers must operate in such harsh, artificial environments that seem almost impossibly extreme. Superconducting qubits operate at temperatures near absolute zero, at temperatures colder than the coldest regions of outer space, colder than anything that exists naturally. Trapped ion systems operate in ultra-high vacuum, more vacuum than exists anywhere else in the universe. Photonic quantum computers use isolated photons far from interaction with matter, moving through optical fibers or waveguides to avoid scattering and decoherence. All of these approaches are trying to solve the same fundamental problem, keeping the qubits isolated from the environment long enough to complete the calculation before decoherence destroys the entanglement, before quantum becomes classical again. The more qubits you entangle, the harder it becomes to maintain that entanglement. 2 qubits entangled might persist for milliseconds before decohering. 10 qubits entangled might last for microseconds. 100 qubits entangled becomes extraordinarily difficult, approaching impossible with current technology. This is one reason why current quantum computers are so limited, not just because they have few qubits, though that's certainly part of it, but because maintaining entanglement across many qubits is technically very difficult, sometimes approaching impossible with available technology. The decoherence time decreases as you add more qubits. The error rates increase exponentially. The correlations become harder to maintain because there are more ways for the system to interact with the environment, more points of failure, more sources of noise. But this is also why quantum computers are so powerful when they work, when they actually manage to maintain entanglement long enough to do calculations. That entanglement, those global correlations spanning many qubits, that's where the computational advantage comes from. The challenge is building systems where you can create and maintain that entanglement long enough to extract useful results before the fragile quantum state collapses into classical noise. Moving to the hardware level, this is where quantum gates come into play. If superposition and entanglement are the computational principles that make quantum computers think differently, quantum gates are the actual mechanisms that implement that thinking. They're the quantum equivalent of logical gates in classical computers. But they work in completely different ways. Classical logic gates are discrete. You put in a definite input, you get a definite output. A NOT gate takes a 0 and outputs a 1, or takes a 1 and outputs a 0 every single time, deterministically. An AND gate takes 2 inputs and outputs 1 only if both inputs are 1. These gates operate on definite classical states. They process bits. They're straightforward. Quantum gates operate on quantum states. They transform superpositions. They create entanglement. They manipulate the probability amplitudes of quantum states. And this is where the alien nature of quantum computing really becomes apparent. A quantum gate doesn't just flip a bit from 0 to 1. It rotates the quantum state in an abstract mathematical space. It changes the probability amplitudes. It modifies the phases. It creates interference patterns. These aren't operations you can visualize easily, like flipping a switch. They're not moving physical objects around in simple ways. They're manipulations of abstract quantum states, described by wave functions and complex numbers and mathematical concepts that don't map onto our everyday experience. The Hadamard gate is one of the most fundamental quantum gates, and it's a perfect example of how quantum gates work and how they create superposition. A Hadamard gate takes a single qubit as input. If that qubit is in the state 0, the Hadamard gate transforms it into a superposition of 0 and 1 with equal probability. If the qubit is in the state 1, the Hadamard gate transforms it into a different superposition of 0 and 1, also with equal probability, but with different phase. The phase is important. It's the quantum mechanical angle, the relative alignment of the two components. The key point is that the Hadamard gate doesn't just randomly decide whether the qubit is 0 or 1. It creates a genuine superposition, a quantum state that is both 0 and 1 simultaneously, with specific probability amplitudes and phase relationships that matter for interference. Apply a Hadamard gate to a qubit initialized to 0, and you get a superposition where 0 and 1 are equally probable. Apply another Hadamard gate to that superposition, and you get the qubit back to 0. The gate is its own inverse. This reversibility is important. Apply a measurement after the second Hadamard gate, and you collapse the superposition back to a definite classical state, which will be 0. These operations are reversible in a way that classical logic gates are not. You can undo a quantum gate, you can run it backward, you can apply it twice, and get back where you started. This reversibility is fundamental to quantum computing. It's not optional. It's required by the laws of quantum mechanics. Information is never destroyed at the quantum level. Every operation can be undone. Every quantum gate has an inverse. This is different from classical computing, where operations like AND gates are irreversible and information is lost. CNOT gates, or controlled NOT gates, are crucial for creating entanglement between qubits. A CNOT gate operates on 2 qubits. It has a control qubit and a target qubit. If the control qubit is 1, the CNOT gate flips the target qubit from 0 to 1 or from 1 to 0. If the control qubit is 0, the CNOT gate leaves the target qubit unchanged. This is a classical description, but when you apply a CNOT gate to a qubit in superposition, something remarkable happens. The control qubit is in a superposition of 0 and 1. When you apply the CNOT gate, the target qubit becomes entangled with the control qubit. The target qubit exists in a superposition where it's 0 when the control qubit is 0 and 1 when the control qubit is 1. The 2 qubits are now linked. Their states are correlated. This is how you create entanglement with quantum gates. This is the mechanism. The gate creates correlations between qubits. Quantum circuits are built by stringing together sequences of these quantum gates. You start with qubits in an initial state, usually all zeros. You apply Hadamard gates to create superposition. spreading single qubits across multiple states simultaneously. You apply CNOT gates to create entanglement, linking qubits together so they're no longer independent. You apply other gates, like phase gates, to manipulate the quantum state in specific ways, rotating the probability amplitudes, changing the phases. The phases are crucial. This is the quantum part that has no classical analog. A classical computer doesn't have phases, it just has bits. But quantum states have phases, angles in complex number space, and changing those phases changes how the wave functions interfere. You apply more gates, building up increasingly complex quantum states, guided by the algorithm you're trying to implement. Throughout this process, the quantum state remains intact, existing in superposition, with qubits entangled with each other, with phases carefully orchestrated to guide the interference patterns. Finally, you apply measurements to collapse the quantum state and extract classical answers. The whole circuit is designed so that when you measure, you're likely to get the right answer. The depth of a quantum circuit, the number of layers of gates you need to apply, is crucial to the performance of quantum computers. Each gate takes time. Each gate introduces the possibility of error, because no gate executes perfectly. Gate errors are inevitable. Small calibrations are off. Voltages fluctuate. Fields vary. Each gate risks decoherence because the longer the circuit takes, the more time for environmental noise to destroy the quantum state, more time for qubits to couple with surroundings and lose their quantum properties. The deeper the circuit, the more gates you need. The longer the calculation takes, the more likely errors become, compounding and accumulating. This is why quantum algorithms are designed to be shallow, to use as few gates as possible, to minimize both the time and the error budget. Classical algorithms can sometimes be arbitrarily deep, applying billions or trillions of operations in sequence without fundamental limitation beyond computing time. But quantum algorithms must be shallow because the quantum states cannot persist indefinitely. Decoherence sets a hard time limit. The calculation must complete before that limit, before the superposition collapses due to environmental noise rather than controlled measurement, before noise destroys the quantum information you're trying to process. It's a fundamental constraint that classical computers don't face. The connectivity of quantum gates is also crucial to the architecture of quantum computers. In classical computers, you can connect any bit to any other bit. Information can flow freely throughout the system. In quantum computers, qubits are often arranged in specific geometries. A qubit can only interact with nearby qubits. You can only apply a CNOT gate between adjacent qubits, not between distant qubits on the chip. This creates topological constraints on which qubits can become entangled. To entangle distant qubits, you need to apply gates through intermediate qubits, creating chains of entanglement and gates. This limited connectivity constrains the types of quantum circuits you can build and affects the depth of circuits needed to implement certain algorithms. It's a practical limitation that affects how quantum computers can be used. Now we move into quantum algorithms themselves, the actual sequences of quantum gates that encode solutions to problems. A quantum algorithm is fundamentally different from a classical algorithm. A classical algorithm is a sequence of logical operations applied to classical data. You fetch a bit from memory, you check its value, you perform an operation based on that value, you write the result back. Each step is deterministic. Each step follows explicitly from the previous one. You can trace through the algorithm step by step. A quantum algorithm is different. It's a sequence of quantum gates applied to quantum states. It doesn't check classical values at intermediate steps. It doesn't have conditional branching based on intermediate measurements. Instead, A quantum algorithm manipulates the entire superposition simultaneously through interference and entanglement and carefully designed quantum operations. Grover's algorithm is one of the most famous quantum algorithms, and it demonstrates clearly how quantum algorithms think differently from classical approaches. Suppose you have an unsorted database with n items, and you're looking for one specific item that satisfies some condition. A classical algorithm must check each item one by one on average, checking n divided by 2 items before finding the target. With a billion items, you'd need to check 500 million items on average. It's slow. It's not scalable. Grover's algorithm solves this problem using superposition and interference, and it does it in roughly the square root of n checks. With a billion items, instead of checking 500 million, you check about 32,000. This isn't a doubling of speed or even a 1,000-fold improvement. It's a square root speed up. It's a fundamentally different computational approach. Here's how Grover's algorithm works at a conceptual level, and this is where you see quantum computing thinking at its finest. You start by putting all your qubits into superposition, using Hadamard gates, creating a superposition of all possible database indices at once. All n items exist in the superposition with equal probability. You then apply what's called an oracle, a quantum gate that marks the correct item by flipping its phase. The oracle doesn't tell you which item is correct. It doesn't return a yes or no answer. It doesn't output information in any classical sense. It just marks the correct item by adding a negative sign to its probability amplitude. This is the key quantum trick. The oracle exploits the phase, the quantum property with no classical equivalent. Then you apply an amplitude amplification operator that flips the probability amplitudes around the average. This causes the probability amplitude of the correct item to increase, while the amplitudes of all wrong items decrease. You repeat this process several times, and each iteration increases the probability of the correct item, while decreasing the probability of all others. By the time you measure, the probability of getting the correct item is overwhelmingly high. Without the oracle, you just get random items, but the oracle marks the target, and the amplitude amplification magnifies that mark. This is quantum computation at its core. You're not checking items one by one. You're not using classical binary search or any classical algorithm. You're manipulating probability amplitudes through interference. You're amplifying the correct answer while suppressing incorrect answers. You're using the wave-like nature of quantum states to guide the computation toward the solution. And the efficiency comes from the square root speedup, which arises directly from the quantum mechanical principles of superposition and interference. The square root speedup might not sound dramatic, but for large databases it's significant. For a database with 1 trillion items, Grover's algorithm checks about 1 million items instead of 500 billion. That's an improvement from 500 billion checks to 1 million. This is thinking that only quantum computers can do. Shor's algorithm is another famous quantum algorithm, and it shows just how dramatically quantum computers can outperform classical computers on certain problems. Shor's algorithm solves the integer factorization problem. Given a large number, find the prime factors. A classical computer cannot factor large numbers efficiently. For a number with hundreds of digits, factoring becomes computationally impossible. It would take longer than the age of the universe, literally. The mathematics shows this, but Shor's algorithm on a quantum computer can factor large numbers exponentially faster than any known classical algorithm. Not faster by some factor, not faster by 1,000 times or 1 million times, exponentially faster, orders of magnitude faster. It transforms a problem that takes classical computers longer than the age of the universe into a problem that takes quantum computers hours. maybe minutes. Shor's algorithm uses quantum Fourier transforms, another quantum algorithm that exists only in the quantum domain, impossible to implement classically. It exploits periodicity in the factorization problem through superposition and interference. It uses entanglement to create correlations that classical algorithms cannot achieve. The algorithm is a sequence of quantum gates, carefully orchestrated to solve the problem through quantum mechanics rather than through classical enumeration. It doesn't try different factors one by one. It doesn't iterate. It exploits the periodicity mathematically through quantum operations. And because the factorization problem is so important for cryptography, Shor's algorithm is often cited as the reason quantum computers could potentially break current encryption methods. RSA encryption relies on the fact that factoring large numbers is hard. But if quantum computers become powerful enough, Shor's algorithm would make factoring easy, rendering current encryption vulnerable. The variational quantum eigensolver, or VQE, is a more recent quantum algorithm that demonstrates a hybrid approach between quantum and classical computing. VQE uses quantum computers to evaluate certain properties of a system and uses classical computers to optimize parameters. The quantum computer prepares quantum states and measures their energies. The classical computer uses these measurements to adjust parameters and guide the quantum computer toward the lowest energy state, the ground state. This hybrid approach combines the strengths of quantum and classical computing. The quantum computer explores the quantum state space through superposition and entanglement, trying different quantum states. The classical computer uses classical optimization techniques to guide the search, using classical algorithms to decide which parameters to change next. Together, they achieve what neither could alone. VQE is particularly useful for quantum chemistry and materials science, for understanding molecular structures and properties, problems that are fundamentally quantum mechanical and difficult to simulate classically. These quantum algorithms, these carefully choreographed sequences of quantum gates, they work because they exploit the unique properties of quantum mechanics. They use superposition to explore multiple possibilities simultaneously. They use entanglement to create correlations between qubits. They use interference to amplify correct answers and suppress incorrect ones. They manipulate probability amplitudes and phases in ways that have no classical equivalent. They think about problems in ways that quantum mechanics naturally describes, and that's why they can achieve speed-ups that classical algorithms cannot. Beyond Grover's and Shor's, there are many other quantum algorithms being developed and researched actively by physicists and computer scientists around the world. The Quantum Approximate Optimization Algorithm, or QAOA, tackles optimization problems by finding the best solution among many possibilities. Variational algorithms adjust parameters quantum mechanically to find optimal solutions iteratively. Quantum simulation algorithms allow quantum computers to directly model quantum systems, something that classical computers struggle with because simulating quantum behavior classically requires exponential resources. There's the quantum Fourier transform, which extracts periodic patterns from data, decomposing information into frequency components. There's the quantum phase estimation algorithm. There's the HHL algorithm for solving linear systems of equations. Each of these algorithms demonstrates a different way that quantum computing can outperform classical approaches. Each shows a different aspect of how quantum thinking operates. Some are proven to offer exponential speedups. Others offer polynomial speedups. Still others are heuristic, offering good results but without theoretical guarantees. But all of them share a common theme. They leverage superposition, entanglement, and interference to solve problems in ways that classical computers cannot. Quantum algorithm design is itself a specialized art. It requires deep understanding of quantum mechanics. It requires mathematical sophistication. It requires creative thinking about how to map problems into quantum states. A good quantum algorithm must construct the right superposition. It must create the right entanglement. It must apply interference in a way that amplifies the solution. It must do all of this while keeping the quantum state intact, while avoiding decoherence, while using the minimum number of gates. It's not easy. It's not obvious how to design quantum algorithms. Some problems yield naturally to quantum approaches. Others are resistant. Some problems we thought might be solvable on quantum computers turn out not to be, or not to offer significant advantage. But when you find a quantum algorithm that works, when you crack the problem in a quantum way, the results can be revolutionary. But there's an important limitation that can't be ignored. Quantum algorithms don't speed up all problems. They speed up specific problem classes. Problems involving searching unsorted databases, factoring large numbers, simulating quantum systems, certain optimization problems, finding patterns in data, sampling from distributions. For other problems, quantum algorithms offer no advantage over classical approaches. For many everyday tasks, classical computers remain superior. You wouldn't want to use a quantum computer to browse the web or write email or create documents. Those tasks are better suited to classical computers. The quantum advantage only emerges for problems that have a specific structure, but quantum mechanics can exploit. Specific mathematical properties that superposition and entanglement and interference can leverage. This is a fundamental constraint. Not every problem is quantizable. Not every problem benefits from quantum thinking. This is why quantum computers are specialized tools rather than universal replacements for classical computers. They're not better at everything. They're better at specific things. Very good at specific things. Incomparably better at specific things. But not universal replacements. The future of computing is not purely quantum. It's a division of labor where each type of computer handles the problems it does best. Classical computers for general-purpose computing, for the vast majority of computing tasks, for things that matter to everyday users. Quantum computers for specific high-value problems that benefit from quantum speedups. Material science, drug discovery, optimization, finance, cryptanalysis, machine learning on certain types of datasets. These are the domains where quantum computers will likely shine. These are the places where quantum thinking offers genuine advantage. The two types of computing will coexist, complementary, each filling a niche that the other cannot fill well. But even as we acknowledge that quantum computers will reshape specific domains, while classical computers handle the rest, there is something deeper that needs to be understood about why quantum computers are so difficult to build and maintain. There is a fundamental fragility at the heart of quantum computing, a vulnerability that arises from the very nature of quantum mechanics itself. The quantum states that give quantum computers their power are simultaneously their greatest weakness. They are delicate, they are unstable, they are constantly under threat from an invisible enemy that exists everywhere at once and cannot be fully escaped, no matter how hard engineers try. This enemy is called decoherence, and it is perhaps the single most significant challenge facing the entire field of quantum computing today. Decoherence is not something that quantum engineers can simply engineer away. Not some minor technical hurdle to overcome with enough ingenuity and funding and clever design. It's a fundamental consequence of quantum mechanics itself, a consequence of the fact that quantum systems cannot be perfectly isolated from their environment, a consequence of the interconnectedness and entanglement that pervades all of nature. Decoherence is the process by which a quantum system loses its quantum properties and becomes classical. It's the process by which superposition collapses, not because you measured the system, but because the system accidentally interacted with its environment. Imagine that you've carefully constructed a qubit in a perfect superposition of 0 and 1, with the two probability amplitudes carefully balanced, with the phase relationship precisely maintained. The qubit exists in this delicate superposition, containing both states simultaneously, holding the quantum advantage that makes quantum computing possible. But then, almost inevitably, something happens. A stray electromagnetic field passes nearby. A thermal photon collides with the qubit. A tiny vibration travels through the apparatus. An atom in the environment brushes against the quantum state. These interactions are incredibly small, incredibly subtle, but they matter. They matter because quantum mechanics is sensitive to everything. The slightest interaction, the gentlest touch, can cause the superposition to collapse. The quantum state transitions into a classical state. The 0 and 1 are no longer both present. The superposition becomes definite. The quantum advantage evaporates. The timescale for decoherence is called the coherence time, and it's one of the most important metrics in quantum computing. Different physical implementations of qubits have different coherence times. Superconducting qubits might maintain coherence for microseconds to tens of microseconds at best. Trapped ion systems can achieve milliseconds, which is remarkably longer. Photonic qubits can maintain coherence for even longer because photons barely interact with the environment. But all of them, without exception, eventually decohere inevitably. The quantum state cannot be maintained forever. There is always a fundamental time limit. The longer the quantum state persists before measurement, the more likely it is that some environmental interaction will destroy the superposition before you get your correct answer. This creates a fundamental constraint on quantum computing that has no equivalent in classical computing. A classical computer can run for hours, days, years without degradation. A quantum computer must complete its calculation before the superposition decays. It's a race against time, against the inevitable march toward decoherence. Think about what a millisecond means for a superconducting qubit. A millisecond is an eternity in the quantum world. In a millisecond, you could apply thousands of quantum gates if each gate takes a nanosecond. But superconducting qubits decohere in microseconds, not milliseconds. You have perhaps 100 microseconds of coherence time, sometimes less. At nanosecond gate times, you can apply roughly 100 gates before decoherence destroys the quantum state. 100 gates. That's your budget. Your quantum algorithm must be shallow enough to complete in roughly 100 gates, or the quantum coherence will be lost. Some problems require thousands or millions of gates to solve. Those problems are simply not solvable on current superconducting systems, no matter how clever the algorithm is, no matter how optimized the implementation is. The algorithm must complete before decoherence strikes, or else all the quantum advantage evaporates. This is the tyranny of decoherence, the hard limit that bounds what's possible on current quantum computers. And it's not just superconducting qubits that face this limit. All quantum computers, regardless of implementation, face the fundamental constraint that quantum states will eventually decohere. The timeline is different for different systems, but the constraint is universal and inescapable. This is why quantum circuits must be shallow, must have few gates. Each gate takes time. Each gate adds to the total duration of the quantum calculation. The more gates you apply, the longer the circuit takes to execute, the more time passes before measurement. the greater the probability that decoherence will strike and destroy your quantum state. So quantum algorithms are constrained to be shallow by the decoherence time available. You might have a brilliant algorithm that solves your problem perfectly, but if it requires hundreds of gates and your decoherence time is only microseconds, the algorithm becomes useless. The quantum state will collapse from decoherence before the algorithm finishes, and you'll get a random answer instead of the correct one. This is why gate speed is so important in quantum computing. The faster you can apply gates, the more gates you can fit before decoherence takes over. Current quantum computers operate at gate times measured in nanoseconds. Scientists are working frantically to reduce this further, to get faster gates, deeper circuits, longer coherence windows. But the fundamental constraint remains. Decoherence is coming. It's inevitable. The only question is how long you can delay it. Beyond decoherence, there are other sources of error in quantum computing. Calibration errors occur because you can never perfectly calibrate a gate. The voltage applied to create a quantum operation is never exactly right. The laser frequency is never exactly on target. The magnetic field is never exactly the right strength. These small imperfections accumulate. Each gate introduces small errors. After many gates, these small errors compound into larger errors, corrupting the quantum state, degrading the probability of the correct answer. Crosstalk occurs because qubits are not perfectly isolated from each other. When you apply a gate to one qubit, it can inadvertently affect nearby qubits through electromagnetic coupling. The gate you intended for one qubit causes an unwanted operation up and a neighboring qubit. This creates correlations and entanglements that were not part of your algorithm, corrupting the state you carefully constructed. The more qubits you have in your system, the more crosstalk becomes a problem, because there are more pairs of qubits that can couple with each other, more unwanted interactions. Measurement errors occur because reading a qubit is not a perfect operation. Sometimes when you measure a 0, you actually get a 1. Sometimes when you measure a 1, you actually get a 0. These measurement errors mean that even after your quantum algorithm produces the correct answer in the quantum state, the measurement itself can flip the result, giving you the wrong classical output. These errors are not rare. They are not exceptional. They are the norm. Current quantum computers have error rates of around 1% per gate, sometimes better, sometimes worse, depending on the implementation. 1% might sound acceptable, but consider what happens when you apply 100 gates. If each gate has a 1% error rate, the probability that all 100 gates execute correctly is roughly 0.37%. You'll get the wrong answer 99.6% of the time. Scale to 1,000 gates and the probability becomes essentially 0. The quantum computer simply does not work. This is why current quantum computers are limited to shallow circuits with few qubits and few gates. They cannot do anything complex because complex algorithms require many gates, and with current error rates, many gates means many opportunities for errors to occur. This is the fundamental challenge facing quantum computing today. Not the number of qubits, not the speed of the gates, but the error rates, the susceptibility to decoherence, the fragility of quantum states. To actually make large-scale quantum computers work, you need quantum error correction. And quantum error correction is one of the most intellectually demanding problems in physics and computer science. The basic idea is that you take one logical qubit, the qubit that stores the information you care about, and you encode it using multiple physical qubits, perhaps 10 or 20 or 100 physical qubits per logical qubit. You spread the information across many qubits so that even if some of them get corrupted by errors, you can still recover the original information. It's like taking a message and creating multiple copies with redundancy, so that if some copies are damaged, you can reconstruct the original from the remaining copies. Quantum error correction codes do this, but they do it in a quantum way, using the properties of quantum entanglement and superposition to protect the information. The codes are elegant mathematically, they're ingenious, they work perfectly on paper, with no actual errors, with idealized qubits that behave exactly as the theory predicts. But implementing them on real qubits, with real errors, with real decoherence, is vastly more challenging than the theory suggests. The challenge with quantum error correction is that it's fundamentally not free. It requires physical qubits, many of them. It requires quantum gates to implement the error correction operations. Those gates themselves introduce errors into the system. You need to measure the quantum state to diagnose what errors occurred, and measurement destroys the quantum state. To measure without destroying the information, you need clever quantum codes that can extract error information without revealing the data. The surface code is one famous quantum error correction approach that requires a two-dimensional grid of qubits arranged in a specific pattern. Other codes like topological codes and stabilizer codes take different approaches, but all of them share the same fundamental challenge. They require vast numbers of physical qubits to encode a single reliable logical qubit. Estimates suggest you need thousands of physical qubits to create a single reliable logical qubit. Perhaps 5,000 physical qubits or more depending on the error rates. Some estimates are even more pessimistic, suggesting you might need 20,000 or 50,000 physical qubits per logical qubit at current error rates. Current quantum computers have dozens or at most hundreds of qubits. This means that with current technology, building a fault-tolerant quantum computer with thousands of logical qubits would require millions of physical qubits. Millions. No quantum computer today has 1,000,000 qubits. The largest systems have around 1,000, maybe approaching 2,000 in some cases. The gap between what we have and what we need for error correction is staggering. It's a gap that might take decades to close, even with optimistic assumptions about progress. This is the harsh reality of quantum error correction. It's theoretically elegant, it's mathematically rigorous, it works, but it requires a vastly larger number of physical qubits than the number of logical qubits you actually want to compute with. This creates what's called the overhead. For every logical qubit, you need many physical qubits. This overhead is one of the reasons why scaling quantum computers is so difficult. You cannot simply add more qubits and expect better performance. You need an exponentially growing number of qubits to maintain the same error rate as the system grows. Building a quantum computer that is large enough and reliable enough to solve real problems might require millions or billions of qubits. This is why some skeptics suggest that quantum computing might never become practical, not because the theory is wrong, not because the physics is impossible, but because the engineering requirements are so extreme, the overhead is so large, the number of qubits needed is so vast, that building actual machines might be beyond our practical capabilities for decades or centuries. The hardware challenge of building quantum computers is equally daunting to the error correction challenge, and the two challenges are intimately connected. Different physical implementations of qubits have different advantages and disadvantages, different coherence times, different error rates, different scalability prospects. Superconducting qubits are currently the most advanced, the most developed, the closest to practical implementation. They use circuits of superconducting material that operate at temperatures near absolute zero, temperatures of tens of millikelvins, colder than outer space. At these temperatures, Electrical current can flow through the circuit indefinitely without resistance, creating a quantum system that behaves according to the laws of quantum mechanics. The energy levels of the circuit encode the qubit state. By applying microwave pulses, you can manipulate the quantum state, creating superposition and entanglement, and the quantum gates needed for algorithms. Superconducting qubits have coherence times of tens of microseconds at best. Their gate times are nanoseconds. They suffer from crosstalk because they couple electromagnetically with neighboring qubits. They require dilution refrigerators consuming kilowatts of power to maintain the necessary cryogenic temperatures, but they have the advantage of being relatively mature technology, with hundreds of qubits already demonstrated in laboratory systems. Trapped ion systems use single ions, individual atoms, held in place by electric fields. The quantum state is encoded in the energy levels of the ion. By applying laser pulses tuned to specific frequencies, you can manipulate the state, creating quantum gates. Trapped ions have the advantage of extremely long coherence times, reaching milliseconds or even seconds in some cases. Milliseconds. While superconducting qubits have microseconds, trapped ions have milliseconds, 1,000 times longer. They have low error rates because the ions are well isolated from the environment, because the quantum states are encoded in atomic transitions that are naturally very stable. All ions are identical, so you don't have variability between qubits like you do with superconducting systems, where each suffix, a conducting circuit, is slightly different, with slightly different resonance frequencies and slightly different characteristics. But trapped ion systems require ultra-high vacuum chambers to prevent collisions with stray atoms, complex laser systems to generate the pulses that manipulate the ion states, precise frequency control to ensure the lasers are tuned exactly right. They are more difficult to scale to large numbers of qubits because controlling and addressing individual ions becomes increasingly complex as the number grows. You need individual lasers or individual laser beams for each ion, or at minimum ways to address each ion separately. Current trapped ion systems have around 100 qubits at most, and scaling beyond that becomes technically very challenging. But the exceptional coherence times and low error rates of trapped ions make them an attractive platform for quantum computing, especially for algorithms that require long coherence times or very low error rates. Photonic quantum computers use individual photons, particles of light, as qubits. The quantum state is encoded in the polarization or path of the photon. Photons have the advantage of extremely long coherence times because they barely interact with the environment, barely couple with anything. Photons can travel large distances without losing their quantum properties. A photon can travel through optical fiber for kilometers while maintaining its quantum state. Photons can potentially operate at room temperature, eliminating the need for expensive cryogenic cooling that superconducting systems require. But photonic systems have the disadvantage that it's difficult to make photons interact with each other, which you need for quantum gates. Photonic quantum computing faces the challenge of creating sufficient photon-photon interactions to implement quantum algorithms. Photons are notoriously non-interacting. In free space, two photons pass right through each other without affecting each other at all. To make photons interact, you need to place them in special media or structures where their fields can interact, or you need to use linear optical elements and measurement-based approaches that are fundamentally different from gate-based quantum computing. Current photonic systems have fewer qubits but potentially offer a path to room temperature quantum computing, eliminating the need for dilution video Gaussian refrigerators and enabling quantum computers that could be deployed in ordinary laboratory conditions or even in the field. Neutral atom systems use individual atoms held by optical tweezers, tightly focused laser beams that trap the atoms in place. The quantum state is encoded in the electronic state of the atom, in the energy level of the electron orbiting the nucleus. Neutral atoms can be packed densely because the traps are very tight, allowing qubits to be positioned very close to each other. This offers potential for scaling to large numbers of qubits relatively quickly. You can have thousands of atoms held simultaneously in an array of optical tweezers, creating a two-dimensional grid of qubits. Recent neutral atom systems have demonstrated hundreds of qubits, and scaling to thousands seems plausible in the near term. But neutral atoms still face challenges with coherence times, which are shorter than travagrametics, abscions, but longer than superconducting qubits. They face challenges with precise control of individual atoms, with maintaining the trap configuration as you manipulate the qubits, with crosstalk between nearby atoms, where operations on one atom inadvertently affect neighboring atoms. Each implementation has its strengths and weaknesses. The field has not converged on a single clear winner. Different approaches might ultimately be suitable for different applications. Superconducting systems might excel for algorithms that require thousands of qubits, but tolerate moderate coherence times. Trapped ions might excel for algorithms where coherence time is critical and you can tolerate slower scaling. Photonic systems might eventually enable practical quantum networks where photons are transmitted over long distances. Neutral atom systems might offer the best near-term path to thousands of qubits. The diversity of approaches is both a strength and a weakness. A strength because it keeps multiple paths to the goal open, because different approaches might be better for different problems. A weakness because it means none of them has yet achieved clear superiority or obvious path to practical quantum advantage. The concept of the NISQ era, the noisy intermediate scale quantum era, describes exactly where we are today. We have quantum computers with tens to hundreds of qubits. We have gate times measured in nanoseconds. We have coherence times measured in microseconds. We have error rates of around 1% per gate. Some are better, some are worse. But 1% is a reasonable benchmark for where we are. These systems are too noisy to implement quantum error correction effectively. Error correction requires such high fidelities, such low error rates, that our current systems don't meet the threshold. They are too small to solve problems of practical importance. 100 qubits with 1% error rates per gate simply cannot execute the algorithms needed to solve real problems. They are too error-prone to reliably execute long algorithms, but they are large enough to demonstrate quantum effects, large enough to show that quantum computers can outperform classical computers on certain specific tasks, large enough to be genuinely interesting from a research perspective. Researchers have shown quantum advantage on specific tasks, on problems engineered to be solvable on quantum computers, but hard on classical computers. Google's quantum supremacy demonstration in 2019 and 2024 showed that quantum computers can outperform classical computers on carefully chosen problems. But these problems were not practical. They were not real-world applications. They were designed specifically to demonstrate quantum advantage rather than to solve problems anyone actually cares about. The NISQ era is where we have quantum computers that do quantum things, but not yet quantum computers that do useful things. This era will likely persist for 5 to 10 years, perhaps longer, depending on how quickly we can improve coherence times, reduce error rates, and scale up qubit counts. Until coherence times improve, Error rates drop, qubit counts increase, and systems begin to approach the threshold where error correction becomes viable. We will remain in this intermediate stage, where quantum computers are interesting but not yet practical, moving beyond decoherence and error correction into the realm of actual application. Quantum computers are already proving their worth in specific domains, where their unique properties provide genuine advantage. Quantum simulation is perhaps the most natural application, because simulating quantum systems is exactly what quantum computers do best. Classical computers trying to simulate quantum behavior face an exponential wall. To simulate a quantum system with n particles, a classical computer must track a state space that grows exponentially with n. Simulating a system with 100 quantum particles would require tracking a state space larger than the number of atoms in the observable universe. The mathematics is relentless. The exponential wall is absolute. No amount of faster classical computers will ever overcome it. You could have a classical computer 1,000 times faster, 1,000,000 times faster, and you still could not simulate a quantum system with 100 particles. The problem is not the speed of the computer. The problem is the fundamental mathematics of exponential growth. Quantum computers, being quantum themselves, can directly simulate quantum systems without this exponential overhead. A quantum computer can directly simulate the behavior of molecules, the interactions of atoms, the properties of materials, by implementing the quantum Hamiltonian of the system and letting the quantum computer evolve according to the same physics that governs the real system. This has immediate applications in chemistry and materials science and drug discovery. Pharmaceutical companies are intensely interested in quantum simulation because understanding molecular interactions is crucial to drug development. And quantum simulation could accelerate the identification of promising candidates. Instead of synthesizing hundreds of potential drugs in the laboratory, scientists could use quantum computers to simulate how thousands of candidate molecules would interact with disease targets, identifying the most promising ones before any chemistry is done. This could compress years of work into months. Quantum machine learning is another emerging application where quantum computers might offer advantage. Machine learning on classical computers involves finding patterns in data by optimizing parameters through gradient descent or other classical optimization methods. You adjust parameters slightly, evaluate how well the model performs, then adjust in the direction that improves performance. You repeat this thousands or millions of times until the model converges to a good solution. This works but requires many iterations, many evaluations. Some machine learning problems might be solvable on quantum computers using quantum algorithms that explore the parameter space more efficiently. Algorithms that use quantum superposition to consider many parameter combinations simultaneously. Quantum machine learning is still largely theoretical, still being developed, but early research suggests potential applications in classification, clustering anomaly detection, and generative modeling. The real quantum advantage would come from problems where the classical optimization landscape is particularly difficult to navigate, where quantum computers can use their ability to explore superpositions to find better solutions faster. Financial optimization is an area where companies like JP Chase are actively investing in quantum computing research. Portfolio optimization involves selecting which stocks and bonds to purchase in what quantities to maximize returns while minimizing risk. Risk analysis involves estimating the probability of various market scenarios and their potential impact. Time portfolio values. Pricing derivatives involves calculating the fair value of complex financial instruments given current market conditions. All involve finding optimal solutions among vast numbers of possibilities. Quantum optimization algorithms like QAOA and quantum annealing might offer advantage on these problems, potentially reducing the time and cost of financial computation. Banks and financial institutions are testing quantum computers on these problems now, trying to understand where quantum advantage might emerge, trying to position themselves to benefit when quantum computers become practical enough to deliver real financial value. Optimization problems in general are considered a likely early application area for quantum computers. Many real-world problems reduce to optimization. Supply chain management involves routing vehicles to minimize delivery time and fuel cost. An optimization problem. Airline scheduling involves assigning aircraft and crews to routes to maximize efficiency. An optimization problem. Manufacturing involves allocating resources to machines to maximize output while respecting various constraints. An optimization problem. Telecommunications networks involve routing data through the network to minimize latency and maximize throughput. An optimization problem. Protein folding involves finding the configuration of a protein that minimizes its energy. An optimization problem. Traffic flow optimization (ON) involves adjusting traffic light timing to reduce congestion. An optimization problem. All of these are optimization problems, problems of finding the best solution among exponentially many possibilities. Quantum computers might eventually solve these better than classical computers, providing real economic value. Some of these problems are NP-hard, meaning that the time required to solve them grows exponentially with the size of the problem, meaning classical computers simply cannot solve large instances in reasonable time. Quantum computers might be able to solve some NP-hard problems more efficiently, but this is still mostly future potential. Current quantum computers are not yet large enough or reliable enough to solve real optimization problems better than classical computers. This quantum advantage for these applications remains on the horizon, not yet realized. Some researchers are testing quantum computers on small instances of these problems, small versions that classical computers can solve to verify correctness. But the quantum computers are not yet solving the small versions faster than classical computers. That's how far off practical quantum advantage still is. Quantum cryptography and quantum key distribution represent an area where quantum computing is already having real-world impact today, not through quantum computers solving problems, but through quantum properties enabling new forms of secure communication. Quantum key distribution uses the properties of quantum mechanics to create encryption keys that cannot be eavesdropped without detection. If someone tries to intercept and measure the quantum states carrying the key, the measurement inevitably disturbs the state, leaving detectable evidence of the eavesdropping. This offers a level of security that classical cryptography cannot match. Quantum key distribution is already deployed in some real-world systems. Some government agencies and banks are using it, though it has not yet reached mainstream adoption. The technology is maturing, becoming more practical. But there's another reason that the adoption of quantum secure communication is accelerating. Governments and companies are beginning to realize that quantum computers, when they arrive, will be able to break the RSA and elliptic curve encryption that currently protects the vast majority of digital communications worldwide. This is not a theoretical threat. This is a real threat with a timeline. Large-scale, fault-tolerant quantum computers with enough qubits to break RSA 2048 encryption might exist within 10 to 20 years, according to various estimates. Some estimates are more pessimistic and suggest it could happen sooner. Some are more optimistic and suggest ARLIN, but there's a significant possibility that within the next 2 decades, quantum computers powerful enough to break Kerr, rent encryption will exist. This threat has driven governments and standards bodies to begin developing quantum-resistant cryptographic algorithms that would be secure even against quantum computers. The National Institute of Standards and Technology is leading the effort to standardize post-quantum cryptography, developing algorithms that can be implemented on classical computers but would resist quantum attack. Organizations are beginning to adopt these new algorithms to transition their infrastructure to quantum-resistant cryptography to prepare for the arrival of quantum computers that can break current encryption. This is a race against time. Organizations must transition to quantum-resistant cryptography before large-scale quantum computers arrive. If they don't, all the encrypted communications they've collected and stored could become vulnerable to decryption once quantum computers arrive. This creates an incentive to transition quickly, even though quantum-resistant cryptography has not yet been fully deployed. What becomes clear when you examine the full landscape of quantum computing is that we are at a pivotal moment. Quantum computers are no longer purely theoretical. They exist. They are real machines in laboratories around the world, but they are still fragile, still limited, still wrestling with the fundamental challenges of decoherence and error rates. The path forward requires solving extraordinarily difficult engineering and physics problems. It requires dramatic improvements in coherence times, dramatic reductions in error rates, dramatic increases in qubit counts. It requires implementing quantum error correction at scales never before attempted. It requires building systems with millions of qubits that operate with exquisite precision. This is not an insurmountable challenge. The physics is sound. The principles are well established. The path forward, though difficult, is clear. But the engineering challenges are immense, and the timeline for practical quantum advantage is measured in years or decades, not months. In the meantime, quantum computers remain fascinating laboratories for exploring the nature of quantum mechanics, for developing new algorithms, for preparing for the day when quantum computers finally become useful tools that solve real problems better than classical computers can solve them. And fragile, their quantum states collapsing at the slightest disturbance. Yet even within these constraints, even in this early stage where most algorithms cannot run successfully, quantum computers have already demonstrated something extraordinary. They have shown us a glimpse of what becomes possible when you harness the strange rules of quantum mechanics, when you build machines that think in superposition and interference instead of binary logic. They have proven that the theoretical promise is not merely academic. It is real. It is measurable. It is verifiable in actual machines, built by actual scientists working in actual laboratories. Google's Willow processor in 2024 performed a calculation in 200 seconds that classical supercomputers would require centuries to complete. Not years, not decades, centuries. The quantum computer solved in the span of a few minutes what would take humanity's fastest classical machines the better part of a millennium. The classical estimate was roughly 13 septillion years, which is 100 billion times longer than the age of the universe itself. 200 seconds versus 13 septillion years. The ratio is almost incomprehensible. The quantum computer had executed its calculation while you could barely finish brewing a cup of coffee. And a classical computer would still be crunching numbers long after the sun expanded into a red giant and consumed the Earth. This is quantum advantage in its most dramatic form. This is the clearest proof yet that quantum computers do not simply run existing algorithms faster. They solve problems differently, more fundamentally, in ways that exploit properties of nature that classical computers cannot access. They think about problems in ways that classical computers cannot access. They think about problems in ways that classical computers cannot access. They think about problems in ways that classical computers cannot access. They think about problems in ways that classical computers cannot access. It was not a drug to be discovered, a financial portfolio to optimize, a delivery route to plan. It was a test case designed to showcase what quantum computers could do when given the right kind of problem. It was, in essence, a problem created specifically because quantum computers could solve it fast and classical computers would struggle. Some critics pointed out the artificial nature of the benchmark, suggesting that it was not a fair comparison, that real problems do not have this structure. They were right that the problem was artificial, but they missed the profound point. The fact that such a dramatic speed-up is possible, even on an artificial problem, even on a problem specifically designed to favor quantum computers, changes everything about how we should think about the future of computation. If quantum computers can achieve a speed-up of 100 billion times on even a specially constructed problem, what might they achieve on real problems designed by nature rather than by benchmark designers? The answer is not yet clear. But the possibility is electrifying. The path to useful quantum advantage requires not just raw speed on abstract problems, but the ability to solve real problems that matter, problems where even small improvements translate into real economic value, problems that genuinely affect people's lives, that impact how we do business, that change how we understand the world. Optimization problems are considered among the most likely candidates for near-term quantum advantage. They are everywhere. They are fundamental to how modern economies operate. The supply chain optimization research from 2026 showed that quantum computers working alongside classical computers could achieve 12 to 18% cost reductions on logistics problems. 12 to 18% cost reduction. This is not a trivial improvement. This is the kind of improvement that could transform an entire industry. 18% might sound modest in isolation. But in a global supply chain, moving trillions of dollars of goods every year, 18% represents billions of dollars in potential savings. Billions. Consider what that means in practical terms. A shipping company with thousands of delivery trucks spending millions on fuel every month could reduce fuel costs by 18% with better route optimization. A manufacturing company with dozens of facilities and hundreds of production lines could reduce waste by 18% through better resource allocation. An airline managing a fleet worth billions of dollars could reduce operational costs by 18% through better scheduling. Banks managing portfolios worth trillions could improve returns by 18% through better scheduling. Banks managing portfolios worth trillions could improve returns by 18% through better scheduling. Banks managing portfolios worth trillions could improve returns by 18% through better scheduling. Better optimization. These are not hypothetical improvements. These are real, measurable, economically significant improvements that would translate directly to the bottom line. Imagine a company with a fleet of 1,000 delivery trucks, each truck burning diesel fuel, each truck traveling routes that have been optimized as well as classical computers can optimize them. The company has already spent years tuning the algorithms, developing heuristics, training machine learning models to predict traffic and optimize routes. But classical optimization algorithms still cannot find the truly optimal solution because the problem is too large, the search space too vast. A quantum computer could find significantly better solutions, could discover routes that are several percent shorter, more efficient, more profitable. The difference in fuel consumption alone, multiplied across 1,000 trucks operating every day, adds up to millions of dollars per year. The time savings alone, the labor savings alone, The wear and tear reduction on vehicles alone combines into enormous value. This is the kind of advantage that companies will absolutely pay for. This is the kind of problem that will drive adoption of quantum computing the moment the technology matures enough to deliver practical results. And the moment practical quantum advantage arrives, it will change commerce forever. Molecular simulation represents another domain where quantum advantage is almost certainly coming. It is perhaps the most natural application for quantum computers because it plays to their greatest strength. The laws of quantum mechanics govern how molecules behave, how atoms bond, how electrons distribute themselves in space, how chemical reactions proceed, how proteins fold into their three-dimensional shapes. All of chemistry, all of biology at the molecular level, is fundamentally quantum mechanical. Classical computers, trying to simulate these quantum phenomena, must translate quantum mechanical rules into classical mathematics, a translation that introduces approximations and errors. The translation is imperfect, it is lossy, it leaves out details. A quantum computer, being quantum by itself, can directly simulate quantum systems without translation, without approximation, without loss of information. It operates according to the same rules that govern actual molecules. It can model how a potential drug molecule would interact with a disease target directly, giving results that classical simulations cannot match. It can explore reaction pathways, calculate activation energies, predict molecular binding affinities with accuracy that classical computers cannot achieve. Pharmaceutical companies are investing heavily in quantum computing research precisely because they understand that quantum simulation could revolutionize drug discovery. They are not betting on someday. They are betting on soon. Drug development currently costs billions of dollars, sometimes exceeding $3 billion per drug approved by regulatory agencies. The timeline is measured in years, often a decade or more per drug. The path from initial molecular target identification, through laboratory experiments, through animal testing, through clinical trials, through regulatory review, takes typically 10 to 15 years. The failure rate is staggering. For every drug that reaches the market, thousands of potential candidates fail. They fail in laboratory experiments. They fail in animal testing. They fail in clinical trials. The cost of each failure is enormous. The time cost is measured in years. The opportunity cost is immeasurable. All of those resources that failed on that one drug could have been spent on other drug candidates. Even modest improvements in the speed or accuracy of drug discovery would be transformative. Massive transformative. If quantum computers could reduce the development timeline by a single year, that would save companies billions of dollars. If quantum computers could reduce the failure rate by reducing the number of candidates that fail in expensive clinical trials, that would save lives. Drugs would reach patients faster. Diseases that today have no treatment might become manageable. Conditions that today are terminal might become chronic. Answer: Alzheimer's, Parkinson's, the autoimmune diseases that plague millions, the viral infections that have killed countless people, all could potentially be addressed faster if quantum simulation could accelerate drug discovery. This is not speculative. This is not theoretical. This is not blue sky thinking. This is where real money is being invested right now, where major pharmaceutical companies are actively working with quantum computing companies to understand how quantum computers could accelerate their research pipelines. Merck, Roche, Johnson & Johnson, Pfizer, the giants of the pharmaceutical industry have quantum research programs. They are testing quantum algorithms on their computing infrastructure. They are hiring quantum computing experts. They are building hybrid systems that combine classical and quantum resources. They understand that quantum advantage in molecular simulation could be worth billions of dollars, could transform their entire industry, could bring life-saving drugs to market years earlier than would otherwise be possible. Financial optimization and machine learning are also attracting serious attention from institutions with enormous resources. JP Morgan Chase and other major banks are exploring quantum algorithms for portfolio optimization, for risk analysis, for pricing complex financial derivatives. These are problems of immense importance in global finance. A portfolio manager with billions of dollars under management needs to allocate those resources across thousands of possible investments, each with different risk profiles, different expected returns, different correlation structures. The optimization problem is to maximize return while managing risk, to balance growth against stability, to navigate the trade-offs that define modern investment management. The solution space is exponentially large, with 1,000 possible investments and countless ways to combine them in different proportions. The number of possible portfolios is astronomical. Classical computers trying to solve this problem must use heuristics, approximations, simplifications. They find reasonably good portfolios, but not necessarily the best possible portfolio. Quantum computers might be able to explore these spaces more efficiently, finding truly optimal portfolios, discovering allocations that classical algorithms would never discover. The difference in returns compounded over years could amount to enormous sums of money. Risk analysis in banking involves modeling thousands of possible market scenarios, each with different probabilities and different potential impacts. Banks need to understand what losses they might face in a financial crisis. What happens if markets crash simultaneously? What happens if interest rates move unexpectedly? The calculation is complex. It involves simulating vast numbers of scenarios and understanding the probability distribution of outcomes. Quantum computers could potentially speed up these calculations dramatically, allowing banks to assess risk more accurately, to understand their exposure more completely, to make better decisions about how much capital to hold in reserve. In a world where financial crises cascade quickly and can cause trillions of dollars in damage, better risk analysis could prevent disasters. Better risk management could stabilize markets. Pricing financial derivatives is another domain of quantum application. Derivatives are complex financial instruments whose value depends on the price of some underlying asset, on interest rates, on time to expiration, on countless other factors. Calculating the fair price of a derivative requires solving differential equations, running simulations, evaluating probability distributions. Classical computers can do this, but often must use approximations. Quantum computers might be able to price derivatives more accurately, more quickly, revealing opportunities that classical analysis would miss. For a bank trading trillions of dollars in derivatives daily, the ability to price them slightly more accurately could amount to billions of dollars in profit. Machine learning researchers are investigating quantum machine learning algorithms that could accelerate training of certain types of models, that could discover patterns in data that classical algorithms miss. Machine learning involves optimizing parameters, finding weights and biases that minimize some loss function. The optimization landscape is complex. It contains many local minima where classical optimization algorithms get stuck. Quantum computers, with their ability to explore superpositions and use interference to guide the search, might be able to escape local minima, might be able to find better solutions. Some quantum machine learning algorithms could potentially train models faster or produce models that perform better, or both. The applications range from image recognition tests, natural language processing, to financial forecasting, to medical diagnosis. If quantum computers could improve machine learning even modestly, the impact would be enormous, because machine learning is already transforming nearly every industry. The applications are not yet mature. The quantum computers are not yet large enough or reliable enough, but the research is advancing. The algorithms are being developed. The frameworks are being built. The convergence toward practical quantum advantage is happening, even if the timeline remains uncertain. The pieces are moving into place. Scientists are writing code that will run on future quantum computers. Engineers are building better hardware. Companies are preparing their infrastructure for the quantum era. When quantum advantage finally arrives, it will not be a surprise. It will be the culmination of years of careful research and preparation. Yet alongside this genuine promise of quantum advantage sits a harsh reality. Current quantum computers are still fundamentally limited by decoherence and error rates that make most real applications impractical. The NISQ era, where we find ourselves now, is characterized by systems that are too large to ignore, but too small and too unreliable to solve truly important problems. We have achieved machines that can demonstrate quantum effects, but we have not achieved machines that can reliably run the long algorithms needed to solve real problems. Superconducting qubits maintain coherence for microseconds. Trapped ions can hold coherence for milliseconds, but milliseconds is still an eternity compared to how long even modest quantum algorithms need to run. The coherence time is the window of opportunity. Outside that window, decoherence has destroyed the quantum state. The quantum advantage has evaporated. The answer, when you measure the qubits, is random noise. If your algorithm requires thousands of gates and your coherence time is tens of microseconds with nanosecond gate times, you cannot complete the calculation before decoherence strikes. The window is too small. The algorithm is too long. The physics works against you. The quantum state collapses. The answer becomes random. The calculation fails. You measured the qubits and got a meaningless result because the quantum state you so carefully constructed, with thousands of gates, was destroyed by decoherence before you could finish. This coherence time constraint is the fundamental barrier that stands between current quantum computers and practical quantum advantage. It is not a barrier that engineering can easily overcome. It is not simply a matter of building better hardware or throwing more money at the problem. Coherence times are limited by the fundamental physics of how qubits interact with their environment. Every qubit is surrounded by an environment. Heat, radiation, stray electromagnetic fields, vibrations in the hardware, all of these cause decoherence. To improve coherence times requires isolating qubits more completely from environmental disturbances, suppressing noise sources, slowing the rate at which decoherence occurs. All of this is extremely challenging. All of it requires solving physics problems that have resisted solution for decades. The best minds in quantum physics have been working on these problems. Progress has been made, but the progress has been slow and expensive. Error rates present an equally daunting challenge. Current quantum computers have error rates around 1% per gate. Some systems are better, some are worse, but 1% is a reasonable benchmark for state-of-the-art. This sounds acceptable until you consider the implications. 1% error per gate means that on a 100-gate circuit, the probability of all gates executing perfectly is roughly 37%. On 100 gates, you execute them perfectly only about 37% of the time. You get the wrong answer 63% of the time. On a 1,000-gate circuit, the probability of executing all gates perfectly approaches 0.000000 something percent. You would get the right answer almost never. You would get the right ans where perhaps once in 10 million trials. On a million-gate circuit, the probability is so small, it is essentially zero. You would never get the right answer. You could run the circuit a billion times and never see the correct answer emerge. Classical computers achieve error rates closer to 1 error per billion operations, or better. In some cases, even better than that. Quantum computers are roughly 1 million times worse in terms of error rates. We have gone backward by a factor of 1 million compared to what classical computers achieve. To make quantum computers practical, error rates need to improve by orders of magnitude. They need to drop from 1% to perhaps 1/10,000%, or better. This improvement is theoretically possible through quantum error correction. But error correction itself introduces new challenges. It requires additional qubits. It requires additional control electronics. Each additional gate and each additional qubit introduces additional opportunities for errors to occur. You might use 1,000 physical qubits to create a single reliable logical qubit through quantum error correction. 1,000 physical qubits to achieve the reliability of one classical qubit. This overhead is not small. This overhead is crushing. To build a quantum computer with 1,000 logical qubits that could actually solve real problems, you would need 1 million physical qubits. 1 million qubits. Current systems have at most a few thousand physical qubits. The largest systems announced in 2026 have perhaps 2,000 or 3,000. The gap between what we have and what we need is enormous. It is not a gap we will close in a year or two. It might take a decade. It might take longer. Scaling quantum computers to the size necessary for practical applications remains one of the most difficult engineering challenges in all of modern science. Perhaps the most difficult. Each additional qubit makes the system harder to control. It increases the coupling between qubits. It increases the crosstalk between neighboring qubits. It increases the complexity of maintaining coherence. The control problem grows exponentially. It is not a linear scaling problem. It is not a problem that can be solved by simply repeating the same engineering that worked for smaller systems. Researchers have to manage an exponentially growing control challenge. As qubit count increases from tens to hundreds to thousands, the number of control lines grows. The precision required grows. The infrastructure needed grows. And it grows non-linearly. The difficulty does not increase proportionally with the number of qubits. It increases faster, much faster. Current quantum computers with hundreds of qubits already require elaborate cryogenic systems that look like something from a science fiction movie. Dilution refrigerators cooling the qubits to temperatures colder than outer space. Dozens of control electronics racks managing thousands of individual signals going into the quantum processor. Precision wiring and shielding. Careful isolation from environmental noise. The whole system looks like a sophisticated laboratory instrument. It is not something you could put in a data center. It is not something that scales easily. Scaling to thousands of qubits would require facilities larger, more complex, more expensive than anything that exists today. The facilities would need to be buildings dedicated entirely to a single quantum computer. The power consumption would be enormous. The cooling requirements would be enormous. The space requirements would be enormous. Everything grows dramatically. Scaling to millions of qubits seems almost unimaginably difficult with current approaches. Some researchers are genuinely skeptical that it will ever become practical. Not because the physics forbids it, the physics allows it. Not because the theory is wrong, the theory is correct, but because the engineering requirements might exceed what is practically achievable. The overhead might be so enormous, the system so complex, the cost so prohibitive, that quantum computers never become useful tools for practical computation, despite the theoretical promise. The path from laboratory demonstration to practical technology is much longer and harder than people often assume. The fact that something is theoretically possible does not mean it will ever become practically deployable. Yet despite these daunting challenges, despite the difficulties that loom before us, the research continues with remarkable intensity. The promise of quantum advantage, even if decades away, is enough to drive enormous investment and effort. Companies and governments worldwide understand that quantum computing will eventually transform certain domains. The race is on to achieve that transformation first, to be the leader when quantum computers finally become practical. To be the nation or the company that controls quantum computing is to control the future in some very real sense. IBM is pursuing superconducting qubits, with roadmaps targeting systems with thousands of qubits within the next decade. IBM has been working on quantum computing longer than anyone. They have the most experience, the deepest expertise, the most developed infrastructure. Google continues advancing superconducting systems while exploring new architectures and hybrid approaches. Google demonstrated quantum supremacy. They have shown they can beat classical computers on specific problems. They are pushing hard to convert that supremacy into practical advantage. IonQ and other companies are developing trapped ion systems, betting that the superior coherence times and low error rates will eventually overcome scalability challenges. They are pursuing a different path, a bet that quality trumps quantity, that having fewer but more reliable qubits will eventually win the race. Neutral atom companies like Quira and Pascual are building systems with hundreds of atoms and ambitious roadmaps for thousands. Ye believe neutral atoms offer a path to rapid scaling. Photonic companies are exploring room temperature quantum computing, betting that photons, which barely interact with anything, might be the key to quantum computers that do not require extreme cooling. Multiple companies are pursuing topological qubits based on exotic quantum states that promise robustness against errors, betting that fundamentally different physics might be the solution. The diversity of approaches reflects the fact that the path forward is not yet clear. The winning technology might be superconducting. It might be trapped ions. It might be something we have not yet invented. Different technologies might ultimately prove superior for different applications. The financial markets might use trapped ion quantum computer. Drug companies might use superconducting systems. Optimization might be best served by neutral atoms. No single technology might dominate everything. The next 5 to 10 years will be absolutely crucial for determining which approaches succeed and which fall short. We will see if superconducting qubits can scale to thousands while maintaining acceptable error rates. We will see if trapped ions can overcome scalability challenges and achieve thousands of qubits with acceptable control complexity. We will see if neutral atoms can maintain coherence and control at larger scales and at the speeds needed for practical algorithms. We will see if photonic systems can overcome the fundamental challenge of photon-photon interactions and create gates that are fast enough and reliable enough. We will see if quantum error correction can be implemented at scales where it actually improves rather than degrades performance, where the overhead is worth h, the improvement in reliability. These are not theoretical questions anymore. These are engineering challenges that will be addressed in laboratories and companies around the world over the coming years. The companies and researchers who solve these challenges first will have a tremendous advantage. They will have systems that work better, that are more reliable, that can solve real problems. They will have access to the capabilities that all other organizations need but do not yet have. The era of quantum supremacy on abstract problems will give way to the era of quantum advantage on practical applications. The future of quantum computing depends on successfully navigating multiple challenges simultaneously. Coherence times must improve dramatically. Error rates must drop dramatically. Qubit counts must scale dramatically. Error correction must become practical and efficient. Algorithms must be developed that exploit quantum advantage on real problems. Classical and quantum computing must learn to work together seamlessly in hybrid architectures. All of this must happen, and it must happen at a pace fast enough to validate the enormous investments being made. Billions of dollars are being spent on quantum computing research and development. This funding is not infinite. Companies and governments will eventually demand results. They will eventually demand practical applications, real quantum or death, advantage actual value delivered. If that value does not materialize soon enough, funding might dry up. Projects might be cancelled. The momentum might be lost. If all these challenges are solved, if quantum computers eventually achieve the promise that theory suggests is possible, the transformation will be profound and far-reaching. Encryption as we know it will become obsolete, requiring rapid transition to quantum-resistant cryptography before malicious actors can use quantum computers to decrypt historical data. Drug discovery will accelerate dramatically, bringing new medicines to patients years earlier than would otherwise be possible. Financial markets will operate with new efficiencies, new risks, new opportunities. Optimization problems across all industries will be solved more effectively, generating economic value worth trillions of dollars globally. Material science will advance as quantum simulation reveals new possibilities. Creative Parker-I, NG. New materials with properties we cannot currently imagine. Energy systems might be optimized more efficiently. Manufacturing might become more precise, more efficient, more sustainable. The world of computation will be fundamentally different. The landscape of technology, business, science, and society will be reshaped. But if quantum computers prove harder to scale than expected, if error rates refuse to improve despite decades of effort, if the overhead of error correction proves too crushing to overcome, if practical quantum advantage remains perpetually out of reach, forever just beyond the horizon, then the quantum revolution might never arrive. Quantum computers might remain laboratory curiosities, fascinating demonstrations of quantum mechanics, but never practical tools for solving real problems. The enormous investments might yield no practical return on investment. The researchers might spend decades pursuing a goal that physics ultimately forbids us from achieving. This is the risk. This is the possibility that keeps some skeptics awake at night. This is why skepticism exists alongside optimism in the quantum computing community. Both perspectives are justified. The theoretical promise is real. The engineering challenges are also very real. The outcome is genuinely uncertain. We do not know which future we are moving toward. What remains certain regardless of quantum computing's ultimate fate is that quantum computers represent one of the most fundamental challenges to how we think about computation, about information, about the nature of thinking itself. They force us to confront the strangeness of quantum mechanics, to grapple with superposition and entanglement and measurement, to accept that reality, at quantum scales, operates according to rules that seem to contradict our everyday intuitions about how the world works. Classical computers think in ones and zeros, in definite states, in deterministic logic, unfolding step by step. Quantum computers think in superpositions and probabilities, in multiple states existing simultaneously, in quantum interference that amplifies correct answers and suppresses wrong ones, guiding computation towards solutions. They think differently, they compute differently, they reveal a side of nature that classical computation cannot access. Whether quantum computers ever become practical tools or not, they have already changed how we think about information, about computation, about the relationship between mind and matter. They have opened our eyes to possibilities that seemed impossible. They have pushed the boundaries of what computation means. As we look forward into a future where quantum computers might eventually become as ubiquitous as classical computers are today, we are embarking on a journey into genuinely new territory. We do not know where this journey will lead. We do not know whether quantum computers will transform the world or remain specialized research tools used only by advanced organizations. We do not know how long the journey will take, whether we are decades away or centuries away. The challenges are severe. The timeline is uncertain, but the potential is enormous. That potential is enough to drive one of the most ambitious technological efforts of our time. Quantum computing forces us to expand our understanding of what computation is, what is possible, what the universe allows us to do. It reminds us that intelligence and thinking are not limited to the binary world of classical computers, to the zeros and ones that have dominated computing for 70 years. In the quantum realm, nature computes in ways we are only beginning to understand. And soon, perhaps within your lifetime, we might learn to harness that quantum thinking to build machines that think the way the universe does at its deepest levels, to solve problems that have remained beyond our reach for generations. That day is still ahead of us, but it is coming. Maybe not tomorrow, maybe not in 5 years, but coming nonetheless. This has been our journey through the strange and beautiful world of quantum computers, through the fundamental differences in how they think compared to every classical computer that has ever existed. You have traveled through superposition and entanglement and quantum interference. You have seen how quantum computers approach problems in fundamentally different ways. You have understood why they are so difficult to build, why decoherence and error rates pose such daunting challenges, why the path to practical quantum advantage is so steep and uncertain. If you have enjoyed exploring these quiet mysteries of quantum mechanics and quantum computing, I invite you to like and subscribe so you can return whenever you wish to contemplate more wonders of science and technology. You can share your thoughts below. Let me know what aspect of quantum computing fascinates you most, what applications you hope to see developed first, whether you are optimistic or skeptical about the future of quantum computers. Your perspective matters. Your voice adds to the conversation. Until next time, may your thoughts be clear and your understanding deep.